that's my many cents on this.
Yeah, thank you, Matthias. Okay, so so that was that. So recommendations to model the Huffenpuff process is essentially what I've been saying for the last half an hour or an hour. So just going to go through the sort of the summarizing steps. So again, Huffenpuff needs, and here it says SRV. That's we changed it to SV because it's shattered rock volume and stimulated rock volume are not necessarily the same. So we threw away the rock part of it, but we're referring to the same thing here. Huffenpuff, it needs a shattered rock volume or shattered volume with small enough pieces such that mixing of injection gas and reservoir fluid is substantial or complete within the rock for the duration of the injection period and subsequent soaking period, if you have one. Okay. The main uncertainties is the size, the shattered volume, and the size of the rubble, the distribution. These two are hard to get, and we completely acknowledge that. It's not like so you may have to do assumptions, you may have to do, or not may, you have to do sensitivities on this, coming up with different distributions. Now, there are proposed techniques of how you can estimate this, the size of rubble. I think there's a bunch of papers by a guy called Acuna in Chevron. He has developed a sort of an RTA theory to do this. And of course, you have all the more expensive measurements and microseismic fiber optics, all these things. And then recovery from the rubble. So how do we model the recovery from the rubble, or how can we determine that in any way? Well, that's what the core experiments are for. And especially doing core experiments on different rock sizes so that you can get a suite of different pieces of the recovery from different pieces. If you, yeah, like I said, it's unlikely that these pieces are exactly the same size everywhere. So you should try to capture at least some of them to get a trend for how this will behave for different sizes. And then you can always extrapolate that as you please. And modeling of those core experiments, it requires a tuned equation of state. That's important. And molecular diffusion treatment. And how do you do that? Well, diffusion coefficients can be calculated from a constant volume diffusion experiment. There is a reference to that here, or using correlations. And the most common one for diffusion coefficients is sigma. Although it's probably not that accurate, it's still very largely used for that purpose. Okay, so here is just some results that we did a couple of years back. We did some simple modeling just to see whether this was even possible to do with any. So it's sort of recreating the experiments that were performed in this paper number 1 referred here. I think that's a paper by a gentleman called Gassimi, along with Curtis and some co-workers of me and Matthias. And the point here is essentially that you have this model, this core model. This is a core plus core holder. So the red line here shows the grid boundary, or the interface between what inside here is core and the outermost row here and column here of cells is the fracture. So you set up the experimental setup. You inject from the top. You can make it vertically or you can make it horizontally. But just to make it vertically, you get a gravitationally stable profile. I've just turned the plots here 90 degrees to make it easier to put into a PowerPoint. But the point here is that here you can see gas saturation profiles, and how it behaves if you do reservoir simulation of this setup. And this setup here it was based on that paper I just mentioned, and also a couple of these papers that has come out of EERC, the core modeling there. They're very transparent about how the cores are, how the core holders look, and so forth, operations and these things. So I think there's some dimensions here, there's saturation, but what you can see here is that there is actually some transient here as well. But so here there's no soak, and here there's a 96-hour soak. And you can definitely see that soaking has an impact. It drives diffusion goes on here for a longer period of time. Of course, 96 hours is much, much longer than the ERC experiments, so there's something we're not getting right here. But the intent was never to match those experiments particularly. It was just to see if it's actually possible to build a reservoir model that can do this type of modeling, and it is. So, and we're also doing some pressure cycling here. We're cycling between 1,000 and 5,000 pounds. Okay, so the well scale model. Again, to minimize numerical dispersion, I is using a large number of grid blocks. One will have to employ some degree of symmetry on the well model. At least that's our view on it and our opinion on it right now. And it has been an opinion by many for many years. Of course, now that computers become more powerful every day, that might change. And at some point, you'll probably be able to model the whole thing within hours. But again, this 12 million grid block example was just showing the magnitude of the number of grid blocks you will probably need to do EOR modeling that is not full of numerical dispersion. And of course, coarse gridding around yields high numerical dispersion. This is just a cartoon of coarse gridding. This is a cartoon of fine gridding. With the logarithmic distribution of grid blocks around the shatter volume to minimize the recovery in the unshattered rock. So here we say piston improperly captured. So the piston is sort of the discretization smears out the sharp front. So that's what we mean by that. And here pistons properly captured. It should probably quote unquote and round properly also, but that's just the idea. So this is what I'm trying to talk about, is piston. If you haven't made a mental image of it yet, maybe this helps. So this is a cartoon that, and we'll see some real simulation pictures later, but the idea is that if this is your displacement profile, and they often look like this, you have this tail of oil, very heavy oil, and you get this sharp front, and then you have the reservoir fluid in front. So back here you have reservoir gas. It's oil saturation plotted against X dimension. So it's a still frame in time. So the oil saturation goes from 0. It's very, very low. This here can be 1 to 2% maybe. If this is the condensing vaporizing mechanism, it might look like this. Also for the vaporizing gas drive, it looks like this. The difference between those is that the condensing vaporizing gas drive also has a condensing part of it in front here. That's not really the point. The point here is simply that if you're trying to capture this continuous sharp front with a discretized grid, you have to think of each cell is an average value of the curve in that cell, right? So you see, for a flat curve, it's easy. You could have made the entire thing here one grid block and it would still be the same number. But once you come over to the sharp front, you see this number here is supposed to represent everything from there to there. So it's definitely a mixing, and that's a mixing. If you're not getting the oil saturation right, that's because you're not getting the composition right. You're artificially mixing oil and gas here to give you an oil and a gas that's not really what you're seeing. But on a very fine scale, you can capture this quite accurately. But if you have a coarse grid, you see this zone of mixing, which is drawn with this gray line. That's the physical region of mixing, we call it. This is where all the multi-contact magic happens. If you make the grid blocks too big, you artificially enlarge that zone of mixing. That's what we're trying to get at there. It's not a beautiful picture. It's not very nice at all, but it's just a cartoon trying to show what discretization does to a model, and especially what it does if you're trying to discretize something that's supposed to be vertical. Okay. So dual porosity models assume pseudo-steady state transfer between matrix and fracture. That's one of the reasons why EDFM has come about. The inadequacies of dual porosity to model even depletion in tighter conventionals is actually an argument for why EDFM came about in the first place. Still, we've chosen to use dual porosity just because there's more in the literature about EOR modeling and dual porosity, again referring to these Ecofisk papers, and particularly this one by Keith Coates. But we acknowledge that this may not be a valid assumption in unconventionals, especially if these sugar cubes starts to become big. Then pseudo-steady state transfer means that the pressure is not transient over a day or whatever simulation term you're using. You're supposed to have developed a steady state picture in if you freeze time. That's not necessarily the case. Using a dual porosity model to represent the shattered rock volume or shatter volume without knowing the potential recovery from different rubble sizes may cause large recoveries due to numerical dispersion. i.e. the SRV size is too big and or the rubble size distribution is wrong. Again, this is something you have to do sensitivities on. And with everything else in this world, you have a P10, P9, P50, P90. It's like reserves estimate, right? You have to have an optimistic, a pessimistic, and a distribution in between. Dual porosity region should be limited to the region of rubble that has experimentally shown a yield of incremental recovery. That's a bold statement, but what we're trying to say is that not necessarily all rock pieces are going to give you recovery. That's what this dimension is given. If you have to set the boundary somewhere. So even though you may have shattered rock outside what you call the shattered rock volume, that boundary is drawn because that's where the limit goes for EOR modeling, for where you get recovery from huff and puff. But depletion-wise, those fractures around or outside that boundary may actually contribute to the depletion modeling. And that's a little bit this confusion with stimulated rock volume and shattered rock volume. The stimulated rock volume has a tendency to include everything that affects permeability and flow performance, but shattered rock volume is more capturing the region where you can expect to get some huff and puff recovery. And that's not necessarily everywhere fracture goes. There is a dimension to this. That is important. Yeah. Okay. Everything else should be modeled by single porosity with fine graining to avoid numerical dispersion. This we know. Okay. So this is a paper, a very good one, but you have to read it 10 times to understand it. That's the drawback of it. But okay, I'm gonna give you. If Matthias lets me, I can go through page by page and talk about this, but I think we'll skip that.
I have to rest.
It's we're broadcasting from Norway here, and it's 10:15 p.m. here, so we're getting tired. But the point here is that what this paper tries to tell you is that it debunked, or well, debunk is a strong word, but it challenged the established truth that dispersion breaks down miscibility in the reservoir on field scale. So if you displace from one well to the next, and there are two, say 3 miles apart, then displacement breaks down before it reaches the producer. But if the wells are 500 feet apart, you get displacement, you get piston efficiency all the way. The idea was that because there are heterogeneity in the reservoir, well patterns, these things that affect what is called conformance, because the recovery profile, if you do a tracer test, if you inject tracer into one well, tracer is fully miscible with the reservoir fluid, and you produce it from the neighbor well, you would suspect that if it were a piston between those two wells, you would suspect that once that tracer hits the producing well, the tracer concentration in the production profile would go from 0 to 1, bang. Okay, if the piston displacement theory applies, that's what you would expect, but it doesn't do that. It gradually increases, and it can take a lot of time before you actually get full tracer concentration in the well, in the producing well. So, and because of this, it was thought that, okay, well, the dispersion effects in the field are much, much larger than the dispersion effects in a slim tube. Because in a slim tube, you do get, if you inject above the minimum miscibility pressure for multi-contact, you get 100% recovery, essentially. You get 99 or 95, but essentially that. So the argument was that, okay, well, if we use coarse grid blocks, we smear out the displacement front, and we essentially choke down the effect of displacement. And then there was theories about pseudo MMPs that were higher than the true MMP. There's a lot of papers here that's interesting to read, but this paper here says that all this is wrong. And that's a very bold thing to say. It was initially published, as you can see here, it was introduced in a conference in 2004 by Keith Coates here and Curtis and Thomas. But it was actually Keith Coates, I think he fought with the SPE for 3 or 4 years to get it into the SPE journal. It is published in the SPRE, but it took a while to get it there because it's a strong paper, and it argues against a lot of people. But the point here is that the displacement efficiency, the miscible front in the displacement process doesn't break down. It's just that heterogeneity and well patterns makes the streamlines go through path of least resistance. Okay, so wherever the streamlines goes, you have 100% recovery. But that, if you look at aerially where those streamlines are, that can be 10% of the reservoir. So the aerial sweep efficiency is 10%. And we always have to remember that an EOR efficiency is a multiple of the displacement efficiency aerially, the displacement or the sweep efficiency aerially, the sweep efficiency vertically, and multiple times the displacement efficiency. The displacement efficiency for miscible processes is 1, but if you have 5% vertical sweep efficiency and 10% aerial sweep efficiency, it's still not a very good process. But that's conformance. It's conformance issues. So the point here is that this paper, and I really encourage you to read it, but the paper says modeling conformance as dispersion. It talks about when numerical dispersion can be modeled, used to model physical dispersion. What degree of numerical dispersion can you put into a model to capture the true physical dispersion? And then again, what is the true physical dispersion? Okay, and that was probably 5 minutes more than I should, but yeah. Again, I encourage you to read it. And by the way, as it says there, all our papers that's been published ever by any employee or previous employee in Whitsun can be accessed on our webpage, free of charge. So you can read it all there, including this one. Key takeaway. So what I've been talking about is simply that, okay, first you model the core experiments, you perform the core experiments, you history match them, then you tune the dual porosity grid blocks, you build a well scale model, you populate the static model with the right Robel distribution, you simulate huff and puff on that well model, and you evaluate the results. And then you might have to go in a loop on these 3 last stages here, but that's essentially very high level. That's the procedure that we're advocating for.
Good. So I think at this point, Stian, we'll take a break for 10 minutes, and then we'll do the last piece, which is hopefully okay and easy to digest. Some field results that should be interesting for everyone, and then some frac-to-frac displacement related things also in the end. And we'll just flip to so I'll just flip to my screen in the break, and then we'll get started in 10 minutes.
I see there is a question here. Let's just do that quick. So from slide 215. So from slide 2, for the first stage, what quantitative data information do you need from the core flood experiments to history match with reservoir simulator? Yeah, so there I would say the more the merrier. If you've done any reservoir simulation, you know what a reservoir simulator requires to do anything. You need initial state of the core, so you need to know with a high degree of certainty what's the initial saturations of the core, what's the fluid system in the core. So you need a fluid model to do that.
The porosity.
permeability, porosity, relative permeability if it's possible. But obviously, you have somewhere along the line here, you have to make assumptions because not all that data is going to be available. But as much as you can get for as many dollars as you have, the better. Okay, I would say.
Yeah. I think for just to make it a little bit less hand waving for the audience in terms of the ERC experiments, what we have there is essentially, when it comes to petrophysical properties, we have the dimensions of the core that's available. We have the initial saturations of oil, and then essentially assuming that the rest is water and air. Permeability measurements are done. Porosity measurements are done through like MISIP type of measurements. The reservoir or the fluid composition that we introduce in the cell, the injection gas composition that we have in a cell, the pressure and temperature, except for that, you need to make assumptions, I guess. But there shouldn't be much left there from that point down in terms of call it rock plug characterization, right?
No.
Be like. No, it'll be like relative on top of curves, but
the rest of the things you need is of course you need a diffusion model. The whole point of that exercise is the more you know about the rock and the reservoir properties you need to put into the reservoir simulator, the more the more accurate because the outcome of the history match is tuned diffusion coefficients. That's what you want to regress on. So when you set up the problem, you have the laboratory, you have the plots from the laboratory, you start doing core modeling. What you want to regress on is the diffusion coefficients in some systematic way. For example, calculating them first by the Sigmund correlation and then applying a common multiplier to all the coefficients so you scale them equally. That's one way. Of course, you can play with some diffusion coefficients. You can go to the literature. Diffusion is becoming more and more acknowledged in the industry as a very important driver for huff and puff. And there are just at this ERTEC in my session, there were a paper doing diffusion coefficient estimation from NMR. I know there are some guys at Penn State University who's doing molecular diffusion coefficient measurements. And all of this work is very appreciated. There's very little of it in the literature that's relevant, truly relevant for unconventionals. But it seems now that people are acknowledging the molecular diffusion importance and are acting on that in terms of measuring diffusion coefficients. So hopefully within a couple of years there will be much more available data on that. At least I'm crossing the fingers on that. So
good stuff. So we'll take a short break and then switch screens, and then it's late for many people, so we'll try to make the last part